Hi folks, Chris McClure. We are now going to talk about dealing with rational expressions. Rational expressions are nothing more than fractions of polynomials, where you have one polynomial divided by some other polynomial. For example, this one right here. Okay. Look, just treat these just like you would fractions of numbers. You can reduce this fraction by canceling any common factors between the numerator and denominator. So you completely factorize that polynomial in the numerator and the one in the denominator. Notice that there's a common factor of x plus 2, so you can cancel that x plus 2, leaving you just with this simplified fraction. It's all good, just provided that you don't divide by x being equal to -2 or -1, because this polynomial in the denominator is going to be 0 when x is equal to -2 or -1. Okay, moving along here. So let's get some practice in reducing these fractions here. These fractions, aka rational expressions. Again, you want to completely factorize the numerator and denominator. That x cubed minus 8, per our discussion a couple of sections ago, that's the difference of cubes, right? Think about that 8 is 2 cubed. So factorize it as x minus 2 times x squared plus 2x plus 4. In the denominator, you have, well, you can factor out the x squared, leaving you with x squared times x minus 2. Cancel the x minus 2, leaving you just with x squared plus 2x plus 4 over x squared. There you go. For part B here, again, factor that numerator, factor that denominator. Notice that there's a common factor of x minus 4. Now, 4 minus x is the same thing as the negative of x minus 4, so don't forget to induce this factor of -1 when you reverse the order of subtraction of the 4 minus x to become x minus 4. And now you just have the -2 over x plus 3. Again, making sure that you are not dividing by 0. Okay? Multiply and divide rational expressions just like you do with any other fractions. You know, when you multiply two fractions together, you just multiply the numerators, multiply the denominators, and simplify as necessary. When you take one fraction divided by another fraction, that's the same thing as taking that first fraction multiplied by the reciprocal of that second fraction. So we invert and multiply. So same concept here for rational expressions. Over here, the first example here, we'll just multiply these two top polynomials, multiply the two bottom polynomials, and cancel any common factors. All right, so one good thing that you could do is completely factorize all of the polynomials so you can identify any common factors and go ahead and divide them. In this case, you might as well just have a single fraction bar, and make sure that you're seeing that you can cancel x minus 1s and cancel x squared plus 1 as well. So you can see we're canceling the x minus 1 and x squared plus 1, leaving just with 4 times x minus 1 divided by x times x plus 2. And it's okay for you to leave your answer just like this. Or you can multiply it back out again if you want. If you want to multiply it back out again, you'd have 4x minus 4 divided by x squared plus 2x. And that's perfectly acceptable. Now, for part B here, we have one fraction divided by another fraction. So we will take that bottom fraction, invert it, and multiply. So we flip it upside down, completely factor everything, and cancel any common factors. Notice that we can cancel the x minus 2's. Maybe cancel x plus 3's. And then I think that's about as far as we can go. And simplify the rest, okay? There we go. All right, moving along, adding and subtracting fractions. Again, the rules apply regarding common denominator. If you have a common denominator, then you could add or subtract the numerators. So, for example, if you have, these two rational expressions added together, notice they have the common denominator, so you just need to add the numerators. So you just have 2x minus 4 plus x plus 3, and that's really easy to do. No surprises there. Same thing with part B. You're subtracting. You have common denominators, so just take the difference of the numerators. Okay, x minus 3x. Don't forget to distribute that minus operation and combine the x and the minus 3x. So it looks like these two things are the same, so disregard that one. But x minus 3x is equal to negative 2x. So you could leave your answer like this, or you can factor it if you want, like that. Now, if you have denominators that are not the same, then you have to do whatever you have to do in order to get common denominators. If it turns out that one denominator is the negative of the other denominator, then just multiply top and bottom by negative. Recognize 3 minus x is the same thing with the negative of x minus 3. So you could write this second fraction here as the negative of 5 over x minus 3. And now you could just simplify this as 2x minus 5 over x minus 3. Okay? Whatever you got to do to make sure that these denominators are the same. All right, but if your denominators don't have anything in common, then you just may have to go about finding the least common multiple of the denominator. So LCD, lowest common denominator. So, for example, if you have x minus 3 over x plus 4 plus x over x minus 2, and you'll find the least common multiple, lowest common multiple of x plus 4 times x minus 2, well, it'll be the product of those two things. So you'll just multiply the first fraction by x minus 2 over x minus 2, just very similar to what you would do for fractions. And then for that second fraction, multiply top and bottom by x plus 4. So now you have a common denominator of x plus 4 times x minus 2. And the numerator, you can just, multiply out the x minus 3 times x minus 2 plus x times x plus 4. Multiply it out, simplify, collect like terms. Okay, and simplify as necessary. Okay, over here, again, in order to figure out what your LCM of the denominators is, you have to factor. But notice that x squared minus 4, x minus 2 times x plus 2, well, there's nothing in common between the two denominators. So multiply that first fraction by x over x, and that second fraction by x squared minus 4 over x squared minus 4, which doesn't change the value of anything. It just gives you a common denominator. Now in the numerator, we have x squared times x is x cubed, and x squared minus 4 times 1, which is x squared minus 4. And then you just simplify that numerator. You have x cubed minus x squared minus a negative 4, which is a plus 4. And then, you might be asked to leave your answer in factored form. So factor the denominator, factor the numerator if you can, which in this case you can't. Now, least common multiple means that you go through, instead of just blindly multiplying the first fraction by that second denominator, top and bottom, and vice versa for that second fraction, you could go about finding the least common multiple of those denominators. And this is a quick recipe for finding the least common multiple of two polynomials. You factor completely the polynomial in the denominator for each rational expression, for each of the fractions. The LCM of the denominators is the product of each of those factors raised to a power equal to the greatest number of times that the factor occurs in each polynomial. We'll see an example here in a minute. And then multiply the top and bottom of each of the individual fractions by an appropriate expression so that the denominators are the LCM. And then we will add or subtract the numerators that result. So, for example, if you want to find the least common multiple of this polynomial and that polynomial, you want to make sure that they are in completely factored form, which in this case they are. Notice that we have a factor of x, 4, x minus 1, and an x plus 1. So let's look at the number of factors that we have. We have one factor of 4, we have one factor of x, we have two factor of x minus 1, and we have three factors of x plus 1. So our LCM is going to have one factor of 4, going to have one factor of x, and you look at the factor of x minus 1, the greatest number of factors between these two polynomials is going to be 2. So your LCM is going to have two factors of x minus 1. And looking at the factor of x plus 1, there's one factor here and 3 there. So your LCM is going to have 3 factors. It's going to have the greatest number of factors between the two polynomials. So this right here is going to be the LCM. It's a common multiple of both this polynomial and this polynomial. But it's the smallest of all possible common multiples, okay? So I just kind of stepped you through it, so I'm going to go ahead and move on to the next screen here. So suppose then that we want to add these two rational expressions. Well, let's take a look at those denominators. Factor that first denominator, x squared plus 3x plus 2, can be factored as x plus 2 times x plus 1. The x squared minus 1 could be factored as x minus 1 times x plus 1. So now that we've seen the factorizations of the two polynomials, then figure out what the least common multiple is. You know, it's going to contain an x minus 1, an x plus 2, and just one factor of x plus 1. So here's your least common multiple. So that means that we have to decide to multiply this first fraction by x minus 1 over x minus 1 in order to have that least common multiple denominator. And that second fraction, will multiply it by x plus 2 over x plus 2. Again, to have that same least common multiple denominator. So here's our first fraction now with the common denominator of the second fraction. And now we will just multiply out those numerators and add them together and see if you can factor and cancel any common factors between the numerator and denominator, which in this case you can't. So this is as reduced as it's going to get. All right, moving along here. Here's another example. We're trying to do subtraction. Again, we need that common denominator, so let's find the least common multiple of those two denominators. that first denominator can factor as x times x plus 1. Second denominator factors as x plus 1 squared. So the least common multiple is x times x plus 1 squared. So multiply that first fraction by x plus 1 over x plus 1 in order to have that least common multiple of x times x plus 1 squared. And multiply that second fraction by x over x for the same reason. And now you can go ahead and add those two fractions with that common denominator, multiply those numerators, and add, or actually and subtract them in this case, and simplify. Now when we talk about simplifying a complex rational expressions, it's really just a complex fraction that we have a couple different ways that we can tackle. There's two methods right here. One way is to completely simplify the numerator, simplify the denominator, and then treat it as one fraction being divided by another fraction. The second method involves looking at all of the denominators that are in play in the numerator and denominator of the big fraction, and find the least common multiple of all those denominators of the smaller fractions, and then multiply top and bottom of the big fraction by the LCM of the denominators of the smaller fractions, and then that'll just give you, as a result, just a single simplified fraction. So we'll look at both methods. Now here's our first example right here. And using that first method, you can combine those two fractions in the numerator by getting the common denominator, like you see here, and then you have this top fraction divided by this bottom fraction. Means that you take the top fraction times the reciprocal of that bottom fraction and simplify. Okay? Just like you see here. Notice there's a common factor of 2 that we can cancel. Okay? Now, let's take a look at how we would do this using that second method, in which case you would take a look at this fraction of 1/2, this fraction of 3 over x, and this fraction of x plus 3. We have a denominator of 2, x, and 4. So what's the least common multiple of 2, 4, and x? The answer is 4x. So multiply the top and bottom of that fraction by 4x, that you see here. And when you do that, that's going to wipe out all of those denominators in the numerator and the denominator of the big fraction. In the numerator, you got 4x times 1/2. Well, this 4 will cancel with that 2, leaving you with the 2x right here. And over here, you've got 4x times 3 over x. The x's will cancel, leaving you with 12. In the denominator, the 4's will cancel, leaving you with x times x plus 3. In other words, now we just have a simplified fraction, simplified rational expression. Okay? All right, here's another example here. We're going to simplify this. All right? Now, if we're going to use the first method, we will, add the two expressions in the numerator of the big fraction, and add those two expressions in the denominator as well, so that we have one fraction divided by another fraction, and then we invert and multiply. Okay, where we took the top fraction multiplied by the reciprocal of this bottom fraction that you see here. We flipped it upside down, multiplied, canceling a common factor of x minus 2, leaving us with x times x plus 4 over x minus 4. Okay, and we could leave it in that simplified factored form. If we wanted to do a an application problem, we could take a look at this problem that talks about, in an electrical circuit, if you've got two parallel resistors, then what is the combined resistance across this little loop here? Well, suppose R1 is the resistance of this one resistor, and R2 is the resistance of the second resistor. Now, this expression right here is what calculates the combined resistance. So if you were to stick multimeter leads here and here, then what would be the overall resistance for your, as measured by your ohm meter? In particular, suppose that we know that one resistor is 6 ohms and the other resistor is 10 ohms. What is the combined resistance? Well, this is kind of complicated where you have 1 over the sum of the reciprocals of those resistances. Now, you could simplify this fraction by multiplying top and bottom of this big fraction by R1 times R2, like you see here. And that simplifies, as you can see here, to this expression there. So then we can just plug in a 6 and a 10 for R1 and R2, giving us 60 over 16, which reduces to 15 over 4, which is about, 3 3/4 ohms. Okay, so that is it in a nutshell, dealing with rational expressions. Okay, folks, so that's it for today, and I'll see you next time.